Here. Okay, so this is again the Schrodinger quantum model. Just a couple of factoids here. Schrodinger model is based upon what we call the wave-particle duality of the electron. That is, it can function both as a particle in motion, or it can function as a wave, because it acts like a wave when at that size and speed. It produces diffraction patterns. So we can apply statistical mechanics and probability to the concepts of electron energies, and we come up with a field analysis is quantum mechanics. Now, the point of, I gave you not a little odd and end things, how we got to this point last time, but sometimes we get so much, can't see the woods for the trees, and I'm world's worth. What is the importance of quantum mechanics? It gives quantum numbers. So the importance of this, after all the fluff I gave it last time, is quantum mechanics the mathematical methods for applying to the atom give quantum numbers. And quantum numbers, Qn, like that, define the behavior of an electron in terms of 4 quantum numbers. Okay, and so this is the principle, which is given by a symbol N, orbital, L, magnetic or azimuthal, M, and spin, which is M sub s. The principal quantum number tells you the location of the electron with respect to what energy level, or what ring is it in. It has a principal quantum number of 2, that electron's in the second ring somewhere. Okay, orbital has to do with shapes, and that's, you remember from earlier courses, SP, D, and F orbitals, and we'll talk at great length about, here's some of the shapes that electrons sweep out in their orbital spheres, figure 8s, overlapping figure 8s, and multiple figure 8s that you. Magnetic is the orientation in 3 dimensions, and there's a special table. If you have your outline, it's not on this, but it's a little triangular table. And we'll go to it later. Okay, and this is the last one, spin quantum numbers, like there, and there are only 2, and it's plus and minus. It's a plus 1/2 and minus 1/2 is typically the numbers assigned. The plus 1/2 defines clockwise spin, and minus 1/2 defines counterclockwise. Okay, so what our objective is to take an electron out of the atom, pull it right out of the atom, and say, okay, name the 4 quantum numbers. Well, at that point, I jumped over into Chapter 8 and we started working on the alpha-bound principle and electron configurations. Because if I go over there, show you how to do that, and come back, show you how the alpha-bound diagram relates to quantum numbers, piece of cake. Everybody gets it first time through, promise you. Okay. So let's run the alpha-bound diagram. Okay. Electron configurations. Electron configurations are just the location of the electron as it's placed into the structure of the atom. The order of filling of electron orbitals is based upon the Aufbau principle. Very classic type concept. And so the Aufbau principle states. Now, when we talk about order of filling, this little note over here, order of filling, another way to explain that is the building up process. In other words, I have a stack of electrons and I'm taking one at a time and put them in their orbitals. That's a building up process. So the Aufbau principle is defined in terms of the building up process. Okay, so that's why I want you to define that. In the building up of process of electrons entering orbitals, the last electron added goes to the lowest available energy level. The order of filling based on the Aufbau principle is defined in terms of the Aufbau diagram. As we talked about and drew out the last of the end of our work last time. And it is drawn relative to what quantum numbers are and what they provide, what information they provide. So when we talk about quantum numbers, we talk about them in terms of principal, orbital, magnetic, and spin, so that we N, L, M, and M sub s. Now, one of the things you're going to learn as we go through this is that no two electrons, that's called the Pauli exclusion principle. I'll put that in right now because it's very important. It says that no two electrons have the same set of 4 quantum numbers. Okay, that means that the 4 quantum numbers define an energy window for every electron. And no two electrons have the same energy window, so that keeps them apart or keeps them from bumping into one another in the course of their movement about the atom. Now, again, it's based upon the fresh page. The Aufbau diagram that I use starts with the lower energies at the top and works down. I showed you one that worked from bottom up. It's the same. It's just giving you that because the textbooks, different textbooks will publish the different alphabet diagrams, one going down or one going up, but they're applied the same. Okay. First quantum number is the principal quantum number, which tells the location. And we know that there are 7 known rings. So we want to come out here 1, 2, 3, 5, 6, and 7, like that. The N value tells you how many suborbital structures a given ring will have. If you have electrons that you're putting in the first ring, it only has one possibility, and that's an s orbital, big sphere. So the s orbital, or it only has one right there. Now, and then 2 will have 2 sublevels, s and a p. And 3 will have s, p, and d. And 4 will be the beginning of the f orbitals, you'll see out here in a moment. 5 goes out to 5 suborbitals, but we only know of 1, 2, 3, 5 f right there. And so if you get out in here, in a theoretical world, it would go S, P, D, F, G, H, I, J. Okay, so when you start building them up beyond what's known, S, P, D, and F, you theoretically enter, you can have as many electrons you want by this principle, is what I'm saying. And then 1, 2, 3, 4, 5, 6, and then finally 7. So one thing to remember is that the principal quantum number tells you how many possible sublevels. Okay, so check mark that a couple of times. Okay, the first sublevel is S. The second is D's. P's, come on Jay. P's. Third levels are D's. Then we get up to F's. And if we go into the theoretical, G, H, I, and so forth. And I've seen questions come up, what is a 9G2 set of quantum numbers? And so you have to draw this out to G and kind of check around. You don't have that, okay? But these are the ones that are known. Okay, so if we're putting in electrons in orbitals, this is an orbital, and it only has one, and so the first one is an s orbital. So it's a 1s. Well, the second level also has s orbital, but we call it 2. And third will be 3s, and all the way down under this heading s, we have every ring has an s orbital. And p orbitals are the next. Now, since the quantum number, principal quantum number, tells you how many sublevels you have, it'll give you 2, and so therefore you have 2 p orbitals that exist. But is there a p orbital in the first level? No, because it don't hold 1. Okay? Now, in the second level, how many orbital possibilities you have? Just 2. So when the test asks you which of the ones is not possible, and you see a 2d for a electron designation, quantum designation, there's no d orbital out here, so that would not be true. So you can't have electron d orbitals in the second energy level, second ring. So that's what I'm saying. Okay, but all the way down under the p, wherever it starts, every one of them from that point on has a p orbital. So forth. Then the d orbitals arrive about the third energy level and third ring, so we have 3 d's. The 4d, 5d, 6d, and I don't think we have a 7. Okay. F, we'll see a 5f and 4f, excuse me, sorry, 4f and a 5f, and you don't have 6f's and 7f's, nor do you have anything out here. These are theoretical. They're not invented yet. So those that I just put in parentheses, like I say, are theoretical, and you can draw an atom. There's no, you know, it's like putting all the decimals in a calculation. You can do anything you want to on paper, but in reality, this represents the largest possible atom we can construct. Now, the order of filling, this is the low energy end of the diagram, and this is the higher energy down here. And according to the alphabet principle, electrons have to enter the lowest available orbital. So the first electrons go into the S1s. Then they go here to the 2s, then back up to the 2p, 3s, back up parallel, and it comes back through the 3p, 4s, back up parallel of the arrow, and we got 3d, 4p, 5s in that order. Then there's that order, and we'll have that order and that one. And then I don't take you into the theoretical, but you can draw one out there if you wish, like that. So if we put electrons and set it up in this order, this is called an electron configuration based on quantum theory. So some atom X would have, the largest one we can do is if we put in all of these. 1s, and then we come around to 2s, and then it goes to 2p, 3s, 3p, 4s. Now when you get to 4s, look at what happens. Here we have a d orbital before, it'll be a 3d, so we're really dropping back down one principal quantum number to a 3d, and that represents the beginning of the transition elements. And so this is a 4s2 with its counting, but that's a 3d1 right there. That's where you start the third. And so when you go to titanium, you have to start putting in 3ds, and so everything in the transition will be d orbital filling. We'll get to that. Okay, so we've got, and then we go back to 4p and go to 5s and back up to 4d, 5p and 6s, back up to 4f. This is when we hit the 4f's, and the f orbital fillings are the rare earths down here. This is your 4f series right here, this first one. So this is a 4f1, f2, f3, f4, f5, f6, f7, and so forth. So the orbitals are f orbitals here. The transitions are d orbitals. S orbitals are the first two columns right here, and your 6 over here, 6 groups over here are all p filling. So if you have a, if you pick out an element in here, gold, well, this outer shell is going to be filling in the d orbital. If you pick out rubidium here, well, this outer shell is going to be filling in the s orbitals in the first two. If you pick out polonium right there, this outer shell orbital is going to be filling in the p orbitals. And if you pick out, say, uranium, this outer orbital is going to be filling in the f orbitals. So that's the way that relates to this. And we'll try to repeat some of that here in a few minutes and show you the building up relates to that. And you can shorten this thing up a lot. Okay, 6s. Where's my 6s? Here we go. And we'll come back up here to 4f. Got that one. 5d orbital. I know this is exciting, isn't it? 6p and 7s. Come back up. 5f, 6d, 7p. That's the largest element that has ever been invented. Right there. There's the last one in the list over there. Okay? One of the rare earths in that in the end of this thing. Each of these have a maximum number of electrons. Okay? And the s orbital, I'll put it up here. S can hold a max of 2. P can hold a max of 6. D can hold a max of 10 electrons. And F can hold a max of 14 electrons. And so this is the basic electron configuration. It does not show the orientations, and we're going to do that in a minute, not show. So you go through here and you put the number of electrons as superscripts all the way down. Now, I know some of you have already done this in other courses, and I appreciate it. Be patient with those who haven't, and enjoy the review. And those that haven't seen this much, and please pay close attention how we kind of structure. Okay, that's how the outbound diagram relates to writing. This is the biggest electron configuration you can draw, including all of the orbitals and everything. Electron configurations can be written for neutral, cationic, and anionic structures that show the gaining of electrons or the loss of electrons in that electron configuration diagram and so forth. So we'll start with the neutral and then we'll evolve to the ions. I refer to electron configuration summaries just to keep from writing it out every time. ECS, okay? Neutral elements. Okay, so we pick oxygen. So just off the wall, pick oxygen. Now there are different ways to write electron configurations. Now I call this the condensed form, and this is the condensed form. It does not show any expanded suborbitals. Now you'll understand that hopefully in just a minute. The neutral elements, you can have a condensed electron configuration summary. Okay? You can have an expanded electron configuration summary. And the difference is the expanded, this shows suborbital orientations. And then you call orbital diagrams, orbital electron configurations. Okay? And when we write orbital configurations, typically we have a condensed orbital configuration. Electron configuration. Show me. So I'm fixing to show you how to put together 4 different representations of an element based on the Aufbau principle and Aufbau diagram. So okay, and you'll have the periodic table available to you. So you go to oxygen, you find the atomic number. So this is the atomic number, and that equals the number of electrons in neutral element, because that's also the number of protons in the element. So the atomic number, being the number of protons, has got to be equal to the number of electrons to give a neutral element. So what you do now is you start writing out the sequence of the Aufbau, the big one, but you only go out to where you have 8 electrons and stop. So the first representation, that condensed form, I can start at 1s, 2, 2s2, 2p, and I have to stop at 8. So I can put a maximum of 6 here, but I don't need 6. So I put 4. That's the configuration, electron configuration for oxygen. This is the condensed. The expanded configuration shows orientations. We haven't talked about this in detail yet. I've shown it to you, but this is what it means, orientations. When you look at the orbitals that we know about, we have an S. These are all p orbitals. These are all d orbitals, and these are f orbitals. So there's s, p, d, and f. Now you won't have to draw this stuff, obviously, but I want you to know what it means. Now, the way it's organized in here, this has one orientation. The p orbitals have three orientations. It's called a px, py, and pz. The d orbitals, now on this diagram, they show d minus 2, d minus 1, and 0, and 1, and 2. If you look on, I haven't drawn, it's not on that diagram. I'll show you in a minute. I simply take these and go D1, D2, D3, D4, D5. 1, 2, 3, 4, 5. There are 5 orientations for the d orbitals, and 7 for the f orbitals. And I call them F1, F2, F3, F4, F5, 6, and 7, and so forth. That's it. So, how do I take this and apply it to the electron configuration summary? Okay, so we want to say the s orbital, the number of orientations is 1. P, you have 3, and it's called px, py, and pz. Okay, when we talk about px, py, pz, it's just orientations along. Here's one along the x-axis. Here's one along the z-axis, and here's one along the y-axis. That's what we're talking about. D orbitals, we have 5. Excuse me. D1, D2, D3, D4, and D5. Okay. Okay. And the F orbitals, you have 7. 1, 3, 5, 7. And just for giggles, how many would you expect for G if you went through this process? 1, 3, 5, 7, 9, right. And so that's theoretical though, okay? And then on up. And so when we theoretically predict the element that has G orbitals, that G orbital will be based on, will have 9 orientations strung across. But we don't know about those yet, so that's unknown. And I call these F1, F2s, F3s, F4, F5, F6, and F7. So, now that's what the orientations are. So when we look up here at the condensed form up here, S orbital only has one orientation, and we just put an S. I'm sorry, I should have put that in there. S orbital doesn't have an X, Y, and Z. It's a basketball and same in any axis. But if we get to the p orbital, we can write that in terms of an expanded. So oxygen, atomic number 8, and I'll put a bracket out here just to identify it, is 1s2, 2s2, 2, and then I'll have 3 px, py, and pz. Px, py, and pz. Those are the 3 orientations. So you're taking a given orbital and expanding it into its orientations. Now's the time I have to show you one other thing called Hund's rule. In the building up process or filling process, electrons enter suborbital structures by parallel spins. Sorry, I'll do it again. You can only have 2 electrons here. This one has 2, that has 2, that has 2, a total of 6 for p orbitals. This one has 2, that one has 2, 2, 2, 2, total of 10 for the d orbitals. When we wrote the original configuration, we put the superscripts of the maximum that they have. And here, 2 in each one of those gives you 14. Now, like this orbital, you fill the suborbital structure that you had. S, you fill it. Second one, you fill it. Then you get over here, I've still got 4 more electrons to put in. And according to Hund's rule, these electrons have to go in by parallel spins. Now electrons have 2 spins, that's it. Clockwise, counterclockwise. And so that gives them what we call an electrostatic attraction to each other. And that's in bonding, we'll get there. But I've got 4 electrons. So I'm going to put the first one here. The second one will go right there. You don't put 2 in the X. You put the next one in. These 2 have parallel spins. Then you put the third one. And then when you finish that and you have 1 more, you come back and then you refill until you get the entire piece structure filled. And then you go over to the next sublevel that's in the sequence on the Aufbau summary. Now, that is the expanded configuration right here. Now, I want to, let me see. Okay. Now, the orbital diagram shows kind of the orbital in a graphic context, and this is like this. If we're talking about oxygen, 8, oxygen 8, 16, like this, I want to, what we typically write is 1s2, 2s2, 2px, py, pz, 211. So there's your oxygen in the expanded configuration. Now, if you're going to do an orbital diagram, what you do is you make a blank for this 1. You say 1 blank, that'll be your s orbital, and it's holding 2 electrons. The first electron in has a positive spin, and the second one in has a negative spin. So that's what the arrows mean. Now sometimes you'll see people put this like that. Okay, some textbooks use that, but I use this little blank, and so you can see which way the electrons are spinning. So that's a plus 1/2 and that's a minus 1/2, just giving you an idea. Now once you fill that one, you go to the next energy level. That's 2. Okay, so 2s right there. Then you fill it, and so it has 2 in there. Then you go to the 2p. Well, there's 3 orientations, 1, 2, 3. And this one is px, this one's py, and this is pz, like that. Now I got 4 electrons to put in. By Hund's rule, they go in parallel. So the first electron in would be a plus spin. The second one in would have to go into py plus spin, and third one would go in here like that plus. Then when you bring that last one in, it goes in pairing. This is a pair of electrons. One's plus 1/2, one minus 1/2. You can't get any more electrons in there. That's why I tell you a given orientation can hold 2 electrons. Simply because this pairing is stable. That's the most stable configuration of electrons that you can get. And that's a chemical bond. Electrons pair, it's bond. Okay. If they are this unpaired, electrons is referred to as paramagnetic. Please learn that term. It means unpaired electron, paramagnetic. The paired electrons are diamagnetic. Learn that term. So that's just some terminology for what these are saying to us. Okay. Now there's one other form of writing electron configurations, and then we'll take a break. Okay. It's a condensed orbital diagram. You're working over here in the heavy transitions laying around platinum, gold, silver. That's quite a few little 1s, 2s, P's, and D's, and F's, and you just got a big string of things, and it looks like this. Well, what the condensed orbital diagram does is it gets rid of the core structure. The condensed orbital diagram only shows it's supposed to only show the valence shell only. Okay, shows primarily the valence shell. Well, what is the valence shell in these diagrams? Simple enough. This is the orbital structure with the highest principal quantum number, the number out front, 2s and 2p. Well, that's the highest quantum number in the oxygen. So the second energy level is the valence shell. Okay, now I can tell you that. Now here's the oxygen, 1s2, 2s2, 2px, py, pz, 211. Okay, the highest, this first number in here is your n value. N equals 2, n equals 2. Here, this one is ring n equal 1. This is the highest quantum number, so this is your valence shell. It's the outer shell. If you went over and did, I can do sulfur. It's right under oxygen, so it will. Okay, so you have 1s2, 2s2, 2p6, 3s2. 3px, py, pz on the valence shell only. I could expand it back here if I wanted to. So that'd be 211. So there's sulfur right there. Where's this valence shell? Well, it's third level. It's n equal 3 is the valence shell. Now, we're not interested in anything that has to do with the core. If I go to subsequent elements, it just gets longer, right? You understand that? You start getting longer and longer SPs and Ds and Ns. This part of the element is the core structure. We're not interested. It doesn't enter into any chemistry. All chemistry takes place at the valence level. So we ain't interested in anything going on in the core. So what do? We use that previous row's noble gas. Before the third level, if you look, the previous rows, let's see, everything in the third row will be a 3 principal quantum numbers, 3 S's and 3 P's, right through here. But these are 1s2 up through 2s2, 2p6. This is what neon is. Well, I don't want to write all that out, and every time I play with one of these things. So what I'll do is I want to condense the core structure, and what I'll do is I'll just put NE in a bracket like that, and enter 3s2, 3px, pz, 211. And so I have sulfur. is equal to that. And so the previous row's noble gas right here is this core structure. And so to keep from having to write all those symbols out, you want to do this. And since the reactivity is in the valence level, we can write the orbital diagram also that looks just like that. 3s, 3pxyz. And so we have parallel spin entries, and then the final one goes in like this. Well, of course, that one was full. And so this is neutral sulfur. And the tendency, if it just give you a little preview, the tendency is to fill those unpaired positions. And so how many bond sites does sulfur have? 1, 2. And so this will show you immediately where the reaction is going to take place. When you put them in, sulfur has a -2 charge. And if you remember, group 6 typically gains electrons toward the noble gas configuration, and to do so we would have to put into more electrons here and here, and when you do that it becomes a sulfur ion like that. And so this is basically kind of a preview of what we're fixing to do in the next chapter in chemical bonding. But your tendency is to put electrons in there and hook it up with other stuff and so forth like that. Okay, now assigning quantum numbers. When we started this, we go through the historical cross-section of building the models and who did what to get the model, and we came to the Schrodinger model, and I said, okay, it's all based on quantum mechanics. Quantum mechanics produces quantum numbers. Okay, we want to assign quantum numbers. Well, quantum numbers refer, a set of 4 quantum numbers refers to one individual electron. Okay, that's the first thing. Second thing is we're trying to assign principal, orbital, magnetic, and spin quantum numbers. So for a given electron, we want an N number, an L number, an M number, and an M sub s number. Okay? Principal, orbital, magnetic, spin. Okay? If we have, say, hydrogen with 1 electron, okay, and I ask you to write the electron configuration for hydrogen. Okay, it's rather easy. It's 1s1. Okay, this number right there is the N number, the one out front. This one is the L number, believe it or not. S, P, D, and F. S corresponds to a 0, P corresponds to 1, D corresponds to 2, and F corresponds to a 3. If it's a P orbital, I would use a 1. That would be the L quantum number if it was a P. Since it's an S quantum number, I'm going to use 0. Okay? Then if it has a subscript like PX, PY, and PZ, this one doesn't have but one orientation. So you'll see, say, a subscript issue down here if you're working with the F5, that F5 orbital, okay? So that's orientation number, that's your M number. And the superscript here is your spin number, M sub s, okay? If, looking at the spin numbers, MS, if it's a 1 listed there, it's a plus 1/2. So if you have S1, that will have an MS of equal to 1/2. If you have an S2 right there, then you'd have an MS of minus 1/2. That's the only option, because you recall an orientation only 2 electrons. One's plus 1/2, and then the other one's minus 1/2. So that's it for that. Here I've shown you the L quantum number, and it's real easy to get the principal quantum number because it's going to be there. 1, if you have you're working in the second orbital for an electron, it'd be a 2 out in front of it, like that. The only issue is trying to explain the numbers for orientation quantum numbers. Okay, orientation quantum numbers. Draw out, start with the 0 and go 1, 2, 3 minus to the left of 0, and then 1, 2, 3 plus to the right of the 0, and then over here on the left column, S, P, D, and F. Write that out. And we have 3 orientations for the p orbital. We have 5 orientations for the d orbital, and we have 7 orientations for the f orbital. Well, if you look at this, we always start with what we call the pivot 0. I call it the pivot because it's right here in the middle. Come over here, and how many orientations does sulfur? Well, it's just S. You don't have to put an X, Y, Z on it. Okay? Now, this one has 3. You start with one of the P's in the middle here, and put one under -1 and one under +1. And now a label of X, Y, and Z. So if I have a PX orbital, its shape quantum number, L quantum number, is -1. If I have a PY that I'm working with in an electron, it's a 0. Okay, if I have a PZ, its orientation quantum number is +1. I'll show you in a minute. Now, we have 5, we want 5 Ds. Do start in the middle and put 2 on the D here, and then under -2 another D, then over here D, and under here D. Now, the diagram I have here starts with a D0, -1, -2. I just go 1, 2, 3, 4, 5. And that's the way that I'm going to list them on the test. Okay, I got a 3D, 5, 2 electron. And then F, start in the middle and put 3 on the left and 3 on the right. And this is 1, 2, 3, 4, 5, 6, 7. So if I'm working with a F orbital, F7 orbital, its quantum number, L number, is going to be 3. M numbers, not L. M shape is going to be 3. Okay? Now, this refers to the orientations of this diagram. So you can see it now. Okay? Now, if you can see across the top, you can see 0, -1 for all those, -2 for those 2 right there, and -3 for this one on the end. And over here is plus, that's 0, +1, +2s, and +3s. Okay? That's over the 3rd quantum number. All right? So that's the only one we needed to write all 4 quantum numbers. So what I'm going to give you now is a 2px1. And what we want to do is the N, L, M, and M sub S for that. This is a single electron. It's in the 2nd energy level. It's in a p orbital. As a matter of fact, it's in the px orbital. Okay? And is just 1 in that orbital. So N, right here, 2. Okay? The shape SPD 0, 1, 2, 3. So it'd be 1. Remember SPDF, I'll write it again. 0, 1, 2, 3. That's your L quantum number. So we look at a P, it's 1. Now we're talking about PX. So we come up here to PX, right here, go up. Its quantum number is -1. Now since it's a 1 in the superscript, it's +1/2. See how it works? Okay. Now what I give you is the electron designation, and all you got to do is run around it and pick the numbers out relative to the tables. Does that make sense? Okay. All right, let's play with a few and see how we do. Okay. Okay. Maybe it make more sense now a little bit. See, if you have an S here, S corresponds to 0, so what we want to do is put a 0 right there. That makes sense? Okay, great. All right. Mr. Tim, we want to find the orientation number now for that. And you remember it starts with 0, -1, -2, -3, 1, 2, 3, and this S, P, D, and F, like that. So we're looking for an S orbital. So it only has one orientation. So what would be the number?
0.
0. Okay, 0. Now it has a 1 up there. Don, what I put? Plus 1/2 or minus 1/2? You understand? You are Don. What's the spin quantum number? How much? It's either going to be plus 1/2 or minus 1/2. If it's 1 electron up here, it's plus 1/2. If it's a 2, it'll be a minus 1/2. No, you're not listening to me. I say the spin quantum number. There are only 2 of them. It can either rotate clockwise or counterclockwise. If this is a 1, when you'll get given this. If it's a 1 up there, you put a 1/2 plus 1/2 in here. There's no other option. If it's a 2, you put a minus 1/2 where the spin quantum number is. That's all it's got. There's nothing else. You look like a big question mark floating over your head right there. Now, those people I've already called on, don't get lost out there. Now, Abdur, let's come back over here. What's the principle right here? 2. Everybody good? Everything? Okay. Juliana, let's go over here to the shape. All right, we're looking about a p orbital. So which one would we put?
1.
That's correct. Everybody kind of catching on? Okay, these are just the assignments. Okay, Erica, we need an orientation for PY. So we come down here. This is X, Y, Z. So we're here at the PY right here. What would be the orientation?
0.
0. That's correct. And it has 2 electrons in there, Sam?
Where?
If it has 2 electrons, so what would you put in here?
-1/2.
That's right, -1/2. There's only positive 1/2. If it's 1, that means you only have 1 electron in that orbital. -1/2. If you have 2, you put a -1/2. No other options. Okay. Yamina, you're next. What's the principal quantum number here?
3.
Big number out front is your end number. Okay? 3. That's right. Don't make it hard, guys. It's not a calculation. It's just look and see where it is. Okay? Jen, let's see. S. We're doing a D shape. So what number?
2.
That's correct. 2, and we need a D4. Now I have to go 1, 2, 3, 4, and straight up. There's a 3, and 4 is a what? 1. So I have a 1 right there, and Josh, we come across here, and it's a 1 right there. What I put? Yeah, I did say Josh. Plus 1/2. That's right. Okay, see in the picture how we do that? Okay. Okay, we'll go through another set real quick. Start over. Victor, what's the principal? What's the principal quantum number? In the designation, I will give you this. Okay, the big number out front is the N number in here. So what number is that? 4. You put 4 as your quantum number. That means it's in the 4th ring. Yeah, baby. All right, now we got an S orientation. Miss Nicole? No, an S shape, I'm sorry. Here's your L numbers. So if it's an S shape, what do you put?
0.
That's right, 0. You did say 0, didn't you?
Yes.
Okay. Okay. Tim, let's see. We need an S orientation. So it's only 1, and what is that?
0.
That's correct, 0. And we got the second electron in, Don. What do we put right here? -1/2. That's exactly right. Don't make it hard. Don't make it hard, really. Okay. Abdur, what's the principal here on this one?
5.
5, that's right. Okay, Juliana, we got an F orbital. I'm F6. 1, 2, 3, 4, 5, 6 straight up. And what is it?
3.
That 2. 7 would be 3. Okay, see. That makes sense? You okay? Okay. All right. So 1, 2, 3, 4, 5, 6, and straight up, and so it's a 2. Okay. Okay, we got a shape F. Wait a minute. F shape would be 3. I'm sorry, I'm looking ahead. Okay, Erica, let's do the orientation now. The orientation. You're right. I'm sorry, I missed that. It should have been a 3 in there. I see what you meant. I was looking at the wrong table. Erica, what is the orientation here?
Radiate plus 2.
Okay, 1, 2, 3, 4, 5, 6, up to 2. Okay. Now, is the 2 electrons in there, Sam? What do you do?
It's negative 1.
Negative 1/2. That's exactly right. Okay, come back up here. We're going to do this one right here. Yeah?
2.
What's the principle?
2.
2. What's the
2.
2 shape? He's saying 2 right there. And we want the orientation. 1, 2. What is that, John?
Negative 1.
And I'll give the last one, it's say minus 1/2. What's wrong with this one? Why can't you not have that? That is a no-no. Look at your outbound diagram real quick. The principal quantum number says how many sublevels you can have. If it's in 1, you have just one little sublevel out here. If you have 2, you have 2 sublevels. There is no d orbital. See, I have a 2d2 right here. Is there a d orbital shown up here?
No.
This is a not allowed. Okay, that's on the test too. So you want to be careful. You know, okay, I'm working with an F orbital. Yeah, I got all kinds of room, you know. But if you're working for P or D, I might have something that doesn't apply. Now, let's go. Another issue is how many electrons can you put in a given suborbital structure, like a px? 2. Okay? So if I wrote out something like 2s2, 2px, py, and pz, something like that, and I had a 3, 1, 1. What's wrong with that? You can only have 2. See there? If I put a 3 in here, that's wrong. You cannot have more than 2 in a single orientation. All of them together, max, can be 6 for a p orbital. But on test day, which of the following, A, B, C, D, is not allowed, and I'll have something like that in there. And the p can't hold an extra electron. It can only hold 1 up, 1 down. That's it. Okay? One more. Okay. Okay, I'm working with 6 carbon. I'm working with carbon. Okay? It's got 6 electrons to put in. Okay? Everybody good there? From the periodic table, I need 6 electrons. So the first one would go here. The second one, you have to fill up whatever level you're working with, like that. Okay? Now, this one, and I've got 4 more to go. So I've got here, and then here. Okay? Everybody good so far? I got 2 more electrons. Okay? They have to go in by parallel spins, right? Okay. So on the test, they'll have A, B, C, D. Which of the following not allowed? What's wrong with that? Can you do this?
No.
That's correct. No. You can't have 2 same spins in one suborbital. Where would this one have to go? It would have to go over here as a parallel spin. So to correct this, we'd come over here. See the point? And it's just a matter of knowing the normals, because I'm going to throw you some curves, okay? Okay. I know y'all going to knock it out of the park anyway. Okay. Now, in the periodic table, metals versus non-metals and kind of thing. It's going to keep it general in what I'm about to do. Metals, in general, tend to lose electrons, okay, and they form a cation plus, and the configuration is the previous row's noble gas. Okay. Non-metals. Okay, that's 4, 5, 6, 7 groups. Okay, they tend to gain electrons, form anions, negative, and the electron configuration summary is the same row noble gas because it just goes to the end. It fills up to the end. Same row. Okay, so let's take sodium. So the 1, 2, 3 has 2 electrons here, 8 electrons here, and has one outer shell electron right there. Okay, so it prefers to lose instead of gain. So it goes to Na plus, and you've got 2 and 8, and that's a +1 right there just to show you. Now write the configuration for that. Well, sodium in here is the first one in the third row. Okay, so when it loses its electrons, okay, sodium goes to Na plus. Its configuration is going to be 1s2, 2s2, 2p6 right there. That's going to be its configuration because it's only going to have, once this one goes away, when you ionize number 3, you only have the N equal 1 shell, and that's the N equal 2 shell remaining. And the 3 shell was the valence shell, but it lost its electron. So this is how you write that. Okay, you show the loss of the s orbital. Put a parenthesis around it and a plus. Okay. Now on the other end, for the metals, non-metals, say we have chlorine. All right, and it goes to Cl minus 1. So it gains an electron right here. So we'll watch it, 1s2, 2s2, 2px, py, pz. Is it a third row? Yeah. Let me just go ahead and do it. Let me go back. P6. And then the valence would be 3s2, 3px, py, pz. Okay? Now, the neutral element in here would be 2, 2, and 1 right there. Because you only have one, you have 7 outer shell electrons, valence electrons, number 17. Group 7 has 7 outer shell electrons. So you can see the 7 here, 2 and 8, this is a valence shell, highest principal quantum number, right here. So it gains electrons. This core structure is not going to do anything. Okay, so valence shell, you can add +1 electron right there. And so to get that negative, we would change that from a 1 to a 2 and put a negative in parentheses up there. So that's the electron configuration for an anion. So it's gaining electrons. It's also the configuration for the argon on the other end. Okay? Elements tend to gain or lose electrons by the path of least resistance to achieve the closest noble gas configuration. And that's the octet rule. And I'll give you a sneak preview. You'll have this in the back of your mind.